Okay, so now we go to chapter 6. So we will just end the chapter 5 here and then go to chapter 6. So at page this page 186. Okay. So previously we have assumed complete knowledge of the PDF on the H0 and H1. Maybe knowledge about the signal or knowledge about the noise or the variance, covariance matrix, etc. Those things are aggregated as the knowledge of the PDF. But then it allows us to design the optimal signal, optimal detector. So we now turn to the more realistic problem in which the PDF is not completely known. So for example, the radar return from a target will be delayed by the propagation time of the signal through the medium. Right? As a result, its arrival time is generally unknown. A communication receiver may not have perfect knowledge of the frequency of a transmitted signal. Thus, in each case, the signal portion of the PDF will be unknown due to an unknown parameter. So similarly, the noise characteristic may not be known a priori. The noise might be modeled as a white Gaussian noise, but an unknown variance. So such is the case in sonar, in which the noise power depends on environmental conditions which are not known in advance. So the design of a good detectors when PDFs have unknown parameters is therefore of its important. So in this chapter, we will review the common approaches to hypothesis testing problem under unknown situations. Okay, so here's a brief summary, but the summary is kind of a high-level summary, and they are a little bit of more abstract, not that easy to understand. And but later on, we will have some more uh, specific cases. We can take a more detailed look at that. So the approach is to the composite hypothesis testing problem, and their performance is summarized here. So we will just take a quick, brief look at this and then go quickly to the specific cases. So the data has the PDF P of X conditional theta 0 H0 or P of X H theta 0 and H0 under H0 and P of X conditional theta 1 H1 under H1. So the forms of the PDF as well as the dimensionalities of the unknown parameter vectors theta 0 and theta 1 may be different under different hypotheses. So notice that the unknown parameter vector theta 0 and theta 1 may be different. So a generalized likelihood ratio test is to decide H1 if this again this is not actually exactly the likelihood ratio, but it looks like a likelihood ratio. So we will say it's a generalized likelihood ratio test. So we will decide H1 if this generalized likelihood ratio is larger than gamma. And then the problem is we have mentioned that theta 0 and theta 1 could be unknown, right? They could be unknown and could be different. The hypothesis is something to be decided, so it's reasonable to be in the parentheses. But the problem is, how should we deal with this data since they are assumed to be unknown and maybe different, right? So the thing is, we will just do the maximum likelihood estimation for theta I. So for example, we will just maximize P of X, for example, theta 1 under H1, and we, based on our observed data, we assume that H1 is the truth, and then try to find the maximum likelihood estimator for theta 1, and then put it here, okay? And then the same thing applies to theta 0. Then of course, we have not mentioned about the MLE yet, right? So it's kind of maybe a little bit difficult, but just uh, try to understand it. MLE will be discussed in the later part of the semester. It will be a continuous variable to be estimated, so we will call it a maximum likelihood estimator. And the other thing is the Bayesian approach. So the test is to decide H1 if this P of X H1 over P of X H0 is equal to this ratio and then larger than gamma. Then you may wonder one thing. You may wonder how come the theta disappear? The theta is supposed to be inside the PDF, then how come it disappear? This is the identity by Bayesian rule, right? P of X, and if we assume theta to be random variable, they have their distribution P of theta. Then what you can do is you integrate the theta out. As a result, you come up with this P of X conditional H1 without theta over P of X conditional H0 without theta. And again, the theta is integrated here. It's integrated here. And it's assumed to be a random variable. Therefore, it has a distribution P of theta 1 and then P of theta 0, and you kind of integrate it out. So you get something without theta, and you take the ratio, and again it's like a likelihood ratio, but it's like a manipulated likelihood ratio because its theta is integrated out, right, larger than gamma, and then you do that's called the Bayesian approach. Okay, and then the parameter test, the PDF on the H0 H1 is the same. Of course, this is a different model. In here, it's dependent on theta. Now, we just say they are the same, except the value of the unknown parameter is different. So the PDF is denoted by P of X conditional theta. Then the hypothesis test is H0 is this is a different settings for the problem. Okay, here we are trying to distinguish H0 and H1, and they have different set of parameters, and the parameters could be a MLE or it could be a random variable. If you know the distribution, then it's a random variable. Here we will just say the data is dependent on a parameter theta, but the hypothesis is H0 is theta equal to theta 0, or H1 is defined as theta unequal to theta 0. Then of course the general likelihood ratio test will be decide H1 if this likelihood ratio is larger than gamma. Then of course you will try to calculate the MLE of theta 1 under H1. That is, you maximize P when you get your observation P, no, you get your observation X, you calculate P of X of theta, then you calculate the MLE under such setting. And of course, you assume it's not equal to theta 0. And of course, very often you calculate the MLE is not equal to theta 0. It's very unlikely, right? Because it's a continuous parameter. How come you have such a coincidence? It's very unlikely. So you just maximize P of X theta and you assume that it's not equal to theta 0. And then you call the MLE to be theta 1. Then you put it into the the parameter position, and then you take your observation, then you have your observations in here and you calculate probability, and then you set a threshold on the ratio. That's the generalized likelihood ratio. Okay, and then we'll skip this word test. Okay, and then the other thing is the nuisance parameter. If you have a nuisance parameter, nuisance parameter means that it exists in your model, but it's irrelevant. It's irrelevant. So we need a way to deal with it. So the problem says goes like this: the PDF on the H0 and H1 is the same, except that the value of the unknown parameter vector is different. Then the parameter vector is theta equal to, you put it into two parts. One is theta r. Of course, the transpose is just, it's just the way we permutate the the variables, right? It's just the way we permute. It doesn't matter. Oh, okay. The transpose is just, you like it to be a row vector, or you like it to be a column vector. It's just like the way we put it, but it doesn't matter. So the parameter vector is theta equal to theta r transpose, theta s transpose. You put it into two parts. One is theta r, one is theta s. Then theta r is r to 1 and theta s is s to 1. Okay, that's their dimension. The PDF is denoted by p of x condition on theta r and theta s. Then the hypothesis test is theta is equal to theta r0 or theta s. And the hypothesis 1 is theta unequal to theta r0 and theta s. And then the generalized likelihood ratio test is to decide H1 if the likelihood ratio is equal to, is set equal to this and larger than gamma, where theta R1 S1 is a MLE under H1. So it's when you take your observations X, then you put X in the probability density function and you take it as a likelihood, function, and then you maximize it over theta R and theta S, and you come up with theta R1 and theta S1, and you put it here in the numerator. And in the denominator, you calculate the MLE under H0, meaning that you assume theta R0 is known. Of course, it's known here. It's known in our problem setting. And theta S0 is the MLE under theta R0 as a non-R0, and then maximize this PDF over theta S only. So there is a head over here. Okay, then when that ratio is larger than the threshold, then you decide H1. Then, okay, so that's kind of the likelihood ratio approach, likelihood ratio. And then there are other tests like wall test and row test, but those are more related to the information uh, theoretical part. We'll skip some of it. And we go to chapter 6.3, composite hypothesis testing, and we will have some examples. So the general class of hypothesis testing problem that we'll be interested in is the composite hypothesis test. Then as opposed to the simple hypothesis test. Uh, just a second. We're at page 191. So as opposed to the simple hypothesis test in which the PDF under both hypotheses are completely known, the composite hypothesis test must accommodate unknown parameters. The PDF under H0 under H1 or under both hypotheses may not be completely specified. So we will express our uncertainty by including unknown parameters in the PDF. So, for example, if we wish to detect a DC level with unknown amplitude in WGN, then under H1, the PDF is like this, right? Because you have a DC level unknown amplitude A, and as a result, as previously settings, we have a amplitude A that is in also immersed in the noise W. Then as a result, you have A that is unknown, but since it's in Gaussian noise, it's in white Gaussian noise, so it has distribution like this, but the amplitude A is unknown here. So it's not like previously we know A, for example, 1, 2, or maybe 3. We know the value of the A here. The amplitude of A is unknown. Then the PDF is not completely specified. So now you know what a composite hypothesis testing is. We like to know H0 or H1. H0 means no signal. H1 means we have a signal. But even if we have a signal, we don't know what the signal is. We don't know the amplitude of the signal. So we have an unknown parameter in the PDF. Okay, so we can see this slightly differently. The PDF under H1 belongs to a family of PDF. How come? You can think of this A as a family of PDF. In fact, that is a family uh, of a function of A, right? You think of this as a function of A, then it's a whole family of PDF. If A is 1, then this is a PDF. If it's a 1.1, it's another PDF. 1.2, another one after one. So you have a family of PDF. You have a family of PDF. So one for each value. The PDF is said to be parameterized by A. So as I just expressed, could be 1, could be 1.1, could be 1.2, could be any real number. It can even be negative. So in dealing with the unknown parameter, the first step is to design an NP test if A were known. Then if possible, the test should be manipulated so it does not depend on the value of A. So we will use the example to demonstrate the NP test and how we deal with the unknown parameter. We will just stop for a second and then come back.